I did my PhD at the University of Michigan. Then I was at NC State from 2004 to 2007. So I was a full-time assistant professor there for 3 years. Then moved a little bit further south. I had been escaping from Michigan weather. I grew up back in Tehran, Iran, and like warmer weather, so I have been moving south. I'm at Georgia Tech since 2007. There I started this lab called Georgia Tech Bionics, which is in the School of Electrical and Computer Engineering. However, I also have an affiliation with the Biomedical Engineering department over there, and I do collaborate a lot with an excellent medical school in Atlanta called Emory University. So this is a little bit of advertisement for Atlanta for those of you who are considering to come to Georgia Tech or to Emory for postdoc. It's a great environment to do all kinds of research related to these type of topics that I'm going to present to you today. So here is the topic of my talk, and on the tutorial part of it, I spent a good amount of time, maybe half of my presentation time, on transcutaneous power and data telemetry, and what kind of changes the gear a little bit in my presentation in comparison with the two excellent talks you heard earlier this morning, is that instead of looking at wearable devices around your body, now let's jump in. Let's see what kind of devices we can have inside the body for what kind of applications. And in fact, there are more presentations on that will be given later today. Very exciting topic. But because this is a tutorial and a majority of you guys are students, I will go into some of the more challenging parts. I can even say more challenging, but some of the challenges that relate to electrical engineering side of this. It's a multidisciplinary field, as you know, and every single one of these disciplines that need to come together to make these things realities, such as a retinal implant that will be presented later today to be realized. Every one of those are important, but with electrical engineering and integrated circuit design background, that's the part of it that I will be focusing on. And then based on how much time will be left after I go through the details of data and power telemetry to an implantable device, I will tell you a little bit about our own research. So there is ongoing research in my lab, both related to implantable devices such as neural recording, neural stimulation, and the kind of scientific test setups and instruments that we develop for neuroscience research application, not necessarily for humans. And at the end, I will touch on a wearable device that we have been working on. In fact, I started that back at NC State and continued on. It grew to become a very large project, and it's a system called tongue drive system. I have been given a lot of time, so probably I will have time to tell you a little bit about that wearable system, non-invasive system as well. So with this introduction, let me show you a little bit, tell you a little bit about what kind of bands and what kind of frequencies we are talking about when the question is how we can use electromagnetics to communicate with devices inside the body and also power them. You heard a lot from Dr. Mute about the importance of power, and there is an external component to the technologies and devices that I will show you, which very well go under the wearable device category. But every implantable device, except for ultra low power ones, such as pacemaker, has an external component to it. That everything that was said this morning is very much applicable, and that's the synergistic part of what I will talk about and what they mentioned. But then, in addition to that, there is an implanted piece to it that communicates, and in many cases is being powered by that external component. And I will spend most of the time talking about that part. So, because you don't want, it's very obvious that when you have an electronic inside the body, you don't want to break the skin, and you don't have access to that device for an extended period of time, preferably the lifetime of that individual, the host. And when these are your constraints, the power that's available to you inside that device implanted in the body become even more precious. Power is precious on implantable, on wearable devices. It's orders of magnitude more precious when it's delivered inside the body, because the rule of thumb is that as you transfer this power from outside of the body just across the skin barrier, which is, depending on where you implant it, is between 5 to 10 millimeters. In certain applications, the distance is a little bit larger, but that's really the distance, that's the barrier that we are talking about. We don't want to break the skin. That's obvious. It's very problematic for the patient. It can cause infection. It's very problematic for the safety of the device itself, because things tend to break when there are wires involved. So that power inside the body is very important, and the rule of thumb says that as you deliver the power from outside of the body into the body, the temperature at the surface of your implantable device shouldn't increase by more than 1 degree centigrade. So when that's the constraint, that's the limit, because if you do, it's as if the tissue around this implanted device is experiencing fever. So you can handle 1 degree, 1.5 degree fever for a while, but if you go with a 2 degrees centigrade fever for a long time, you start causing damage. You start affecting the tissue and the cells around that implantable device, and you might do more harm than good. With such a harsh and very strict constraint, we have to deliver this power, whatever amount that is needed. For example, in the case of retinal implants, something in the order of 100 milliwatts. How would you deliver 100 milliwatts during the operation of this device to this implanted item inside the body without raising the temperature at the surface of this device by 1 degree? You can imagine how efficient you have to be. The power dissipation should be extremely small across this small distance. And something like this retinal implant, and I give this example because you will hear a lot more about it later today, needs a lot of data as well, because the sensor, the artificial sensor that is replacing the natural sensor happens to be outside of the body, but the interaction with the central and peripheral nervous system happen inside the body. So you have to deliver this visual information in whatever form, very smart form and fashion that you can. You have to communicate that huge amount of information into the body with whatever frame rate you take that image. It's not going to be anywhere close to natural vision, but even a very crude and much lower resolution vision generates a huge amount of information. So consider that limit 1 degree C, and you have to deliver multi-megabits per second of information into this device, again wirelessly across a short range. So the problem is twofold: very efficient power transfer for whatever this electronic device inside the body needs to do, and very efficient and wideband data transfer, because there is a huge amount of information that needs to go into this device. And you look at, for example, brain-computer interfaces. That's another example that a huge amount of information needs to go outside the body. You record from the brain, from the central nervous system, from the motor cortex, where the decisions are being made, and you're dealing with a person that is completely paralyzed. So this person, basically the brain is intact, there is nothing wrong with the brain, that's where the decisions are being made, but you need to find a way to infer what that decision is, because there is no other way to get to access that decision. The decision is that I want to move my arm and press this button. And there is a huge amount of information at the neural level, at the cellular level, that you need to process in order to infer that decision, in order to find out that this is what this person wants to do, process that information, deliver that information to a robotic arm, let the robotic arm does this for him or her, because this person has a spinal cord injury and the rest of his or her body is paralyzed. So there is a need for both of these examples, brain-computer interfaces and retinal implants, need that power. That's taken. Every one of them need between 10 to 100 milliwatts of power, even when you really make it smart and lower the power consumption. Of course, there is still a long way to go, but that's where we are right now. And both of them need a wide bandwidth. The first example needs a large amount of data going into the body. The other one needs a lot of data going out of the body. So with this introduction, we want to use electromagnetics. And this is very different from the type of electromagnetics and the type of data transfer that your cell phone uses. Because the cell phone uses far field. The communication is between the cell phone in your pocket and the cell tower, which is hundreds of meters away. We are talking about something across the skin. And that affects what type of frequencies you use in order to have this power and data transfer, and the wavelengths of that electromagnetic field, and that waves also become very important. So what I will be talking about is basically in this range, inside this circle, radiative and reactive. Both of them are under near field interaction between your antennas inside and outside of the body. If you are between 0 to lambda over 2 pi, your interaction is reactive. The significance of reactive interaction is that you have your antennas tend to look like coils, and the energy is stored around the transmitter within the magnetic field that you create. And the very nice thing about this reactive near field interaction is that energy is not going to be dissipated. The energy is going to return back. It's going to be stored inside that magnetic field. And if you are smart enough about designing this inductive link, part of it will be delivered to that receiver, and the rest of it will return back to the source. That's very nice thing about this reactive interaction. The radiative one is different. If you are further away from that source, then the transmission, which tends to be at higher frequency, the energy will not return to the source, it will be radiated. And there are basically applications, inductive links, when the frequency is between 100 to about 50 megahertz that operate based on reactive interaction. And there is, for example, a very well-known and very useful band that's set aside for medical implant communication services, 402 to 405 megahertz, that uses this radiative type of interaction when, for example, the pacemaker is sending data about something that has happened to the heart activity over the past 24 hours to an external receiver sitting next to the bed. That basically advanced pacemaker uses a mixed band to send that information, because there we are not talking about centimeter range transfer. There we are talking about 1 meter, for example. So keep that in mind also. But the focus of, again, relatively speaking, the focus of my talk will be around this reactive type of interaction in the near field domain. And these are some of the examples of devices implanted in the body that use that type of interaction. And as I said, because there are devices that are that have high average power consumption, such as cochlear implants, retinal implants, and neuromuscular implantable neuromuscular stimulators. And there are devices such as pacemakers or deep brain stimulators that, relatively speaking, they have high instantaneous power consumption, but the rate of activity is much, much lower. For example, in the case of a pacemaker, when it is pacing the heart, during that 1 millisecond, the power consumption is pretty large, but then it needs to pace the heart at, for example, 200 beats per minute. And therefore, the device is asleep, almost no power, like nano power consumption, until the next onset of stimulation. So when you average out, the average power consumption of a pacemaker is about, as it was mentioned, is in the order of 10 microwatt. Therefore, even though about basically more than half of this can is filled with a battery, that battery is a primary battery that would last in most recent pacemakers for about 10 years. When the period of replacement of this device is in the order of 10 years, the power consumption is so low, you can afford to have a primary battery. In the case of deep brain stimulator, it's about 2 years, 2 to 5 years, depending on the needs of the user. The stimulation rate is a lot higher, and therefore there is a big interest in making deep brain stimulators more power, basically less power consuming, because really that surgery is a little bit too frequent, and the way, which is out of the scope of this talk, but now there is a very hot topic about how to make the deep brain stimulators closed loop, how to make them smarter, not to be just a dumb pulse generator, how to set the pulse rate, how to set the specifications of the pulse that you are delivering based on the needs and the activities of the host, the end user. And these are some of the techniques that are also being used in pacemakers, because now they are equipped with accelerometers. If your body needs, it has more activity, they basically adjust the heart rate and so on and so forth. But there are other devices which are basically the stimulation rate is so high, and the space that you have, for example, in the case of a cochlear implant, the whole thing has to be placed inside a bone behind your ear. And you can imagine you don't have that much space over there. Or the retinal implant, everything is, well, not everything, part of it still could be where you implant the cochlear implant device, but part of it is inside the eye, because there is even more size constraint as opposed to the chest area, and more power consumption, because, for example, the average stimulation rate of a modern cochlear implant is in the order of 10,000 pulses, stimulation pulses, some of them even higher, 10,000 stimulation pulses per second through multiple channels. You can compare that with 200 pulses per minute in a pacemaker. Or with retinal implants, I don't know what the rates are. I'm sure Dr. Weiland will mention that in
20 pulses per second.
20 pulses per second in the case of a retinal implant. Okay, so still when you compare that with and that I assume is a low resolution, today's device. If you want to go to higher resolution, obviously you need much more pulses, and that's really the trend that, for example, cochlear implants have gone through, and you will hear more about that. But the power consumption levels are not comparable with that of pacemaker. That is why really placing a battery, and even a rechargeable one, is almost out of question. Rechargeable batteries are being worked on, but you need that continuous delivery of power, because your device, even if it does not consume, and this is not the power consumption of the electronics necessarily, even if we totally ignore the power consumption of the electronics, you just need that much power to be delivered into the tissue, to the surrounding neurons and the tissue, for that effect to take place. Therefore, that's the power consumption, and that's why we need to deliver that much power. And when it comes to inductive power transfer, the implantable devices, the high-power, high-performance implantable devices, are hardly the only applications. In fact, these devices are coming, are already in the market. You can charge your gadgets. There is near-field communication. RFID has been around forever, and rechargeable, wirelessly rechargeable electric vehicles are on the horizon. So more or less, when it comes to high efficiency wireless power transfer, all of these devices and wideband data transfer, all of these other applications can more or less benefit from these techniques that I will present to you today. Now let's go into a little bit more detail. I will present some of the fundamentals of inductive coupling. Just before I go further in there, a little bit more about the choice of frequency. Because the temperature rise is very important, and the temperature rise, one thing I did not mention is that the choice of frequency does affect the temperature rise. Why? Because depending on what frequency you use for your inductive power and data transfer, the rate of absorption in the body, which is more than 90% water, is going to be totally different. As you can see, in this range, it is proportional to frequency squared. It means that if you go from one frequency to a frequency twice as much, the rate of power absorption in the tissue is going to be 4 times higher. You can obviously see how important the choice of frequency is. And if you go to somewhere around, this is about 2.4 gigahertz, somewhere around here, you can actually use that frequency, that electromagnetic field, for the purpose of generating heat. Where do you use that? Nobody has microwave in your kitchen? That's exactly what microwave oven in the kitchen uses. It operates at 2.4 gigahertz for the purpose of generating heat and heating up your food through a wireless electromagnetic field. That's the exact opposite of what we want to do in this human being, because we don't want to cook the tissue under the transmitter coil. As a result, our choice of frequency is very limited. As I said, somewhere between 0.1 to 50 megahertz. That's almost as far as you can go when it comes to wireless power delivery. Forget about gigahertz. You should try to avoid that and go to lower frequencies, because the lower the frequency, as you can see in this steep curve, the lower the frequency, the more transparent the tissue and the water is to electromagnetic field. So lower frequency, more penetration into the body. Higher frequency, more absorption in the body, and what does that energy turn into? To heat. Very dangerous. We try to avoid that. But here is where the challenge comes. The challenge is that, okay, for power transfer, you use low frequency, but when it comes to delivering data through electromagnetic field, there is a direct relationship between the bandwidth, basically how much capacity this electromagnetic link has to delivering data, and the carrier frequency. So you see that you have a huge dilemma on your hand. For high power transfer, lower frequency is better for obvious reasons. for high rate data transfer, high frequency is better because high frequency in communication, even in your cell phone, even in your Wi-Fi uses 2.4 gigahertz for good reasons, because basically there is more bandwidth to use, and this is why with Wi-Fi you can get 100 megabit per second or more easily, but that's not really, we don't have that luxury when it comes to delivering power into the body or sending power sending data outside of the body. So the solution that we came up with a few years ago was to really separate out these two functionalities. One carrier to be dedicated to wireless power delivery from outside into the body, another carrier to be dedicated to wireless data delivery into the body or outside of the body, and that is what is shown in this block diagram. The power transfer link, which operates at a pretty low frequency within that safe box that I showed, is basically responsible to send the power from our RF power transmitter through a pair of coils that form a transformer to our implantable device. Could be a neural recording or a stimulating system. There is some power, very smart, very high efficiency power management involved here. Today I will not have time to go over this block, but actually you can see a lot of that in our publications, because we really try to make this power delivery channel very, very efficient all the way from the source to the load, to the consumer inside the body. And then the link in the middle is for data delivery from outside of the body into the body, again through an inductive link. And I will show you why we chose an inductive link for that forward. This is what I call forward data transmission. Then for situations that you have, for example, a brain-computer interface, you want to deliver a lot of power from brain, from the central nervous system, outside of the body. And you can use, for example, something like mixed band, that 400 megahertz or even higher, because the amount of power you transmit is very, very small. Why it can be very small? Because your external receiver can be very sensitive. If you make your external receiver very sensitive, then you can still use those high frequencies in order to be away from those other bands to transfer a large amount of information outside of the body, and that's the technique we are using. So 3 carriers for 3 different functionalities: wireless power transfer into the body, wireless data transfer into the body, wireless data transfer through back telemetry outside of the body, with very distinct frequency bands. Because what makes this challenging, it might sound simple, but really the devil is in the detail. When you want to bring all of these coils and antennas and electromagnetic fields and put them in a device that is about 1 centimeter cube, it basically tens of PhD theses come just out of that, because it's that complicated. They're minimizing the interference between these electromagnetic fields and designing those antennas and these very high efficiency power and wideband data transfer. There are basically not just in my lab, many researchers all across the world are working on this topic now. So let's move forward. You see what are some of the challenges. Let's look at the power for now. If you want to look at the power, the source of the power happens to be a rechargeable or primary battery that you replace outside of the body. So if you look at the example of a cochlear implant, there is a behind ear piece that has a rechargeable or replaceable hearing aid battery. And then as the power goes in across that 1 to 2 centimeter link, there are a lot of losses down the road. until the good power, which is the power that eventually reaches your electronics. And then after that, the electronics basically deliver that information to the nervous system. For example, in the case of a cochlear implant, there is an array of electrodes between 14 to 24 sites that generate electrical pulses, and then the auditory nerves get excited by those electrical activities and send that information to the auditory cortex, and then the brain makes, after some training, makes sense of those electrical activities, and the person start to hear not a very high quality sound, but good enough for them to have a conversation, for example. And then these are those losses. You need a power amplifier to convert the DC power on the outside, because the power source is a battery. You need to turn it into AC, otherwise it's not going to go through a transformer. So there is loss right there. You need a very efficient power amplifier, and Class E or Class D power amplifiers happen to be very efficient. So you need to design a pretty efficient power amplifier. You have a primary coil. The primary coil that is on the outside of the body. If you have seen anybody using a cochlear implant, usually they hide it behind their hair, but there is a coil on the outside with a magnet in the center of it. That is the transmitter coil. It is wired to this behind the ear device, and then there is a tiny little coil underneath that coil embedded in the bone that I mentioned through surgery. There is another magnet in the center of that coil, and then these two magnets, as they attract each other, they hold the external coil in place and also help with the alignment of these two coils. But that primary coil, because it has internal resistance, when you drive that coil, you dissipate some power. And then there is some power dissipation in the tissue, which is basically that curve that I showed. Thanks to the proper choice of frequency, because we did choose low power frequency, not just us, all these cochlear implant manufacturers choose very low frequency, relatively speaking, for the power transfer. Cochlear implant, Advanced Bionics, Medel in Europe, they choose basically somewhere between 2 to 40 or 50 megahertz for their power transfer. Therefore, the tissue loss is almost negligible. Relatively speaking. And then you have the secondary coil loss, because that coil is not ideal either. It has paralytic resistance, and you have power loss there. These three power losses are very dangerous. These are the power losses that can basically increase and elevate the temperature at the surface of your implanted device above 1 degree C. That's a no-no. So you should be very careful about these power dissipations. Then you have to convert that AC signal back to DC and then clean it up, because your electronics need a very clean and stable power source, a DC power supply, in order to properly operate. So the power conversion from AC back to a stable, well-regulated DC is another, basically any conversion you do, it can't be 100%. So it has some efficiency limitation. At the end of the day, your overall efficiency, all of you have seen in control theory, that when you have some back-to-back conversion, the overall efficiency is going to be the multiplication of all these efficiencies. And this is the challenge, because while you can see that every one of these efficiencies, every one of these conversions can totally kill your overall efficiency. If you have a bottleneck, that can kill your overall power conversion efficiency. Therefore, every single one of these are extremely important. From DC to AC, basically turning it in from current to electromagnetic field, absorption of the electromagnetic field, reception of the electromagnetic field, turning it back to current, converting that AC current back to DC, and then finally your electronics will use that power and do whatever they are supposed to do. Every single one of these steps matters, because the overall efficiency is multiplication of every one of them. Now, I won't go into the detail of self-inductance and mutual inductance. There are books and papers written about this that go back to the days of Tesla, and he was a very big proponent of wireless power transfer, by the way, and people say that he came up with some ideas that unfortunately were destroyed for whatever reason. The reason I put some of these equations and put this slide together is to let you learn at least one point out of this slide, and that is the fact that your self-inductance, which is basically how much magnetic field you can generate based on an AC current, variable current that you create in this coil or push into this coil. And even more important, the mutual inductance, meaning that between the transmitter and the receiver coils, how much interaction you have, they are highly dependent on the geometries of these coils. So the shape of the coil, the number of turns, the type of wire you use, all of these things are very, very important. How these two coils are located with respect to another, are they completely parallel, are they shifted, is one of them rotated? Every one of these geometrical details play a very significant role in basically determining the amount of mutual inductance or self-inductance you have in these coils. So when I talk about optimizing power transfer efficiency, especially if I want to tell you among all these different factors, which ones are the most important one in terms of which one is the bottleneck, actually designing high efficiency, relatively speaking, Class E power amplifiers is relatively easy. Power conditioning inside is you can get more than 80% efficiency there. Here, if you do it right, you can get more than 95% efficiency. The bottleneck is here. The tissue absorption, we can handle that by lowering the carrier frequency. These two guys are very tough to deal with. This is why I say the geometry and the design of the coil is so important, because the efficiency of the power transmission from the primary coil to the secondary coil could be in somewhere between 40 to 60%. Within 1 centimeter distance is highly dependent on the distance as well. So you ask yourself, among all these power losses, where is the bottleneck? Where should I focus and basically go deeper in terms of improving that efficiency? I would say the primary power coil dissipation and secondary power coil dissipation are going to be the most important ones, and that's exactly what I'm going to talk about. We use a technique that is, as I said, is well known. It's called the resonant coupled coils. It turns out that if you, instead of having two dumb coils in front of one another, even two coils alone will couple into one another, and you have a current. When you pass current into the primary, if they are close enough, you pass current, you generate current into the secondary. That's the basis of a transformer. But the interesting thing is that if you add two capacitors to this mix, by the way, these two resistors are inevitable. R1 is the parasitic resistance of L1, and R2 is the parasitic resistance of L2, and R2 is very difficult to manage. Why? Because you cannot use a coil that is like 1 centimeter in diameter and implant it inside the body. That coil is very thin because the volume that you have is very small. Even if I want to really push the size, that coil has to be implemented using micro-machining technology. It should be a planar coil. We don't have enough space for wire. Sometimes, for example, when actually in a cochlear implant or a retinal implant, you can manage to have wire if your wire is very thin and very properly selected. But when it comes to brain-computer interfacing, the space that you have, basically you have a space between the skull and the surface of the brain. We are talking about millimeter size space, or if you can use some of the space into the skull, or something planar on the just below the skin, then your coil is a planar spiral. It has been actually defined using photolithographic techniques, and therefore that resistance is quite significant, and reducing it becomes quite challenging. But the point of this slide is that if I add these two capacitors and resonate my primary and secondary coils, that now, thanks to these capacitors, they are called tanks, resonating tank circuits, I can increase the voltage that will be induced across the secondary by almost one order of magnitude. So this is the frequency response across the secondary when I have resonance. This is how much you get when you don't have resonance. So it's a no-brainer. Of course, you use resonating circuits in order to deliver power. Nobody uses just a simple transformer to do that, because the voltage is going to be much lower. And one more important thing in this slide that the details have already worked out elsewhere. When you look at the power transfer efficiency from the source to the load in this very, very simplified model of our inductive link, these are the most important factors. The most important thing is the coupling coefficient between these two coils. As you can see, it's K squared in the denominator. And what is K? K is actually basically the mutual inductance divided by square root of L1 and L2. So every one of these play a role, but just note that this M is very important, and M is very dependent on the relative positioning and the geometry of these two coils. The other two factors that are very important is the quality factor of the primary tank circuit and the quality factor of the loaded secondary tank circuit. So you can see that all of these are in the denominator, and as an antenna / coil designer, I try to maximize this term. If this term was infinite, then I get perfect 100% power transfer efficiency, but that's impossible. But your goal in designing these inductive links is to maximize the multiplication of these three terms. Another important thing is that the power transfer efficiency, basically the power received divided the power transmitted, is not the whole story. Sometimes you get a very high power transfer efficiency, but the amount of power you receive at the load is dismal. You need, for example, 100 milliwatt. Your coil, your inductive link can only deliver 100 microwatt. It's 3 orders of magnitude less than what you want. And then you would say that, okay, I will boost the primary voltage source in order to deliver as much power as I want. But then who would carry around a transmitter with a 10,000 volt AC? I won't carry that behind my ear or near my ears. So therefore, power delivered to the load is also very important. This is something that sometimes designers, very experienced designers, forget about. That not only power transfer efficiency is very important, power delivered to the load is also very important, because you need a reasonable voltage, let's say 100 volts maximum, to be safe and to deliver enough power to your load. And that load is also very important, because here what you see in this curve is that I use the same coils, the same two coils. I don't change anything. The geometry and all the details of these coils, the number of turns, the diameter, everything, the spacing between the lines, everything is constant. I have listed those in this table. They are out of this journal paper. And the only thing that I have shifted in order to see how my power transfer efficiency changes is that RL. So I change, excuse me. So I change this RL and look at the changes in the power transfer efficiency versus RL. You can see that there is
and a particular RL that based on whatever coil arrangement that I have set in order to get the best possible power transfer efficiency maximizes the efficiency. And RL is very important because my efficiency can change from 10% when the RL is 10 kilo to more than 70%. I didn't change the distance, I didn't touch anything about the coil. The coil are already optimized. If I pushed it as much as I could, and can go back down to only 20% when RL is 10 ohms. Around 200 ohms, with this wireless link, you can get the best power transfer efficiency. Now, what is the challenge with RL? Guess what? RL is variable. Because depending on what, for example, I keep giving the example of retinal implant because I know that my good friend is going to present, tell you the details about this. But when I'm looking at a bright screen like this, the current consumption of that retinal implant will be very different from when I'm in a dark room or when I'm looking at a very dark scene, a very dark image. So your RL is changing, is basically varying all the time, and even though you can set a nominal value, you have to deal with that problem, and my RL may not be where I want it to be. So that is the reason that to address that problem, we need to deal with impedance transformation. And impedance transformation is a trick that electrical engineers and communication engineers use to go from one load value to a desired load value. And there are two ways to do it in an implantable device. You can either use multiple coils or matching circuits. And how do we use multiple coils? For example, you can add an additional transformer between your load and your secondary coil. So imagine that I had this L1 and L2, now here they are called L2 and L3. These are my original coils. But then I add a fourth coil, which is basically coupling onto L3, and I basically choose the geometry and mutual coupling between these two coils in order to have this coil to see this load as if it was an optimal load. And here you can see that if I change that K34, K34 is related to M34. If I change the value of K34, this is the previous two coil curve, efficiency curve. I can turn it into this one. Look at the beautiful flat more than 70% efficiency that I have here, regardless of whether my RL is 10 ohm or 1 kilo. That's very important because RL changes all the time, and therefore I need to stay above 70%. Otherwise, the heat the heat will go up. And then what my students did was to look at how changing the geometry of these three coils affect two parameters, the two key parameters: power transfer efficiency and power delivered to the load. And you can see that we want to be around this area in terms of power transfer efficiency. The problem is that a lot of researchers, a lot of designers forget about this here. So they look at this and say that, oh, I want to be at very high efficiency, and they basically what they don't pay attention to, that the power delivered to the load may not be high enough. What you care about, the best area is that probably here, by even if we need to sacrifice a little bit of PTE not to be at the highest level, but look at this. I can get 3 times more power delivered to the load without changing the source amplitude. That's very important because, as I said, we don't want a 10,000 volt source. We want a 100 volt load, and when I say 100 volt variation, not a 100 volt battery, 100 volt AC voltage across the transmitter coil and be around here. So you can see that this is really the sweet spot that we can get the best PTE and the best PDL. And you probably have heard about this very interesting experiment at MIT. They use 4 coils instead of 3 coils. Basically, they use a transformer on the primary side, then they had 2 huge coils across the room, and then another small coil on the receiver side to deliver about 60 watts of power, 15 to 60 watts of power, the demonstration of how you can wirelessly deliver power across a room. What they did not tell in their presentations and in their papers was that when you use a 4-coil power transfer, which is basically you have one transformation here, one transformation here, we actually have done a lot of experimentation both with 3-coil and 4-coil. You have L1, L2, L3, and L4, and of course your math becomes a lot more complicated, but there is a way which we have shown in the paper to optimize this 4-coil link and get the best power transfer efficiency. The challenge is this, that you get a very good power transfer efficiency, but the power delivered to the load is very, very dismal. And that's the problem of 1000 volts or 10,000 volt source that I was telling you about. So you compare this situation with a 4-coil link and this situation with a 3-coil link, you can see that here you have a nice overlap that you can handle both PTE and PDL. But in this case, unfortunately, where you have good PDL, you don't have good PTE, and then you have good PTE, you don't have good PDL. Basically, that is why we decided to explore this a little bit more, and that resulted in definition of this figure of merit. When as engineers, when we have to deal with multiple optimization parameters at the same time, it's sometimes easier to define a figure of merit. This figure of merit actually looks at both of these at the same time, and not only those, it also looks at the amplitude of your source. These are the important factors when it comes to a wearable device that is supposed to wirelessly power something implanted inside the body. The power, this is PTE, this is the efficiency, power transfer efficiency is important, power delivered to the load is important, and the source amplitude is important. If your source amplitude becomes 10,000 volts, in order to deliver the amount of power that you want, obviously your figure of merit is going to hurt. But if you can deliver a good efficiency and a good amount of power delivered to the load with reasonable source voltage, obviously you get the best figure of merit. And again, I skip over the detail. If you are interested, you can see that, see all the details in the journal paper. And I just wanted to point out that this figure of merit also has a parameter N, which tells you which one you weigh more. Is power transfer efficiency more important for your application, or power delivered to the load? And then by adjusting the N, you can get into the sweet spot and then design your coil accordingly. So we even took into account your application requirements. We compared, for example, what happens if you optimize a coil with respect to power transfer efficiency, power delivered to the load, or with respect to this figure of merit, and then compare different applications. For example, the type of coil design that you need based on this figure of merit for delivering 1 kilowatt to recharge your electric car is very different from the type of coil design you need to power your retinal implant or your cochlear implant. The nice thing about this figure of merit is that it guides you exactly which one of these coil configurations you need. Sometimes 2 coil is the best, sometimes 3 coil is the best, sometimes 4 coil is the best. It gets quite complicated, but because of the definition of this figure of merit, which is applicable to all these 3 different coil configurations, you can reach a conclusion that this is the best choice for my design. And this is basically a sort of highly simplified comparison between 2, 3, and 4 coil links, that where are their advantages and where they are relatively weak in terms of a lot of things, coupling, variation. Something that is very important is that that I didn't mention is that how sensitive is your PTE and PDL with respect to coil misalignment, because really coil misalignment is something that as a designer of that system you have to deal with. You can't say that these two coils are going to be perfectly aligned all the time, because the next time your user will put this coil on his or her body, it could be shifted a little bit, or as I move there is a vibration, and that's out of the scope of this presentation, but we have also built a closed-loop power control system around this wireless link in order to basically make sure that the delivered power to the load is always optimal. Now let's change gears a little bit, and I want to tell you the tricks, some of the tricks in wireless data telemetry as well. So that covered the wireless, well, that introduced you to the challenges and the details of wireless power delivery. Now let's look at wireless data delivery. As I said, in different applications, the need for power in terms of forward power transfer and back telemetry is very asymmetrical. There is, to my best knowledge, I haven't seen an application that needs wideband data transfer in both directions, from inside the body out and from outside of the body in. For neuroprosthetic devices that substitute an artificial sensory modality, for example, cochlear and retinal implant, the big flow of information which requires high bandwidth is from outside into the body. The back telemetry link is actually quite narrow band, and it just checks to see whether things are working fine, whether the temperature is right, whether the neurons are happy, so on and so forth. So that link is not a very heavy load. In brain-computer interfaces, the example of this paralyzed person that I gave you, there is an asymmetric situation. There is a very high volume of data that should go out to get the intention of this person, but then the forward information is not as wideband. More recently, people are talking about brain-computer interfaces that, for example, give the sensation when this robot touches, like I command this robot by thinking about this move to move and grab something, and as it touches that object and applies force, I can actually get a sensation of how much force I'm applying. So that link is also becoming important, but nothing comparable to back telemetry link. So this asymmetric situation needs to be considered when you design the inductive link for data transfer. And in the past, engineers have used the same power transfer link for data transfer. And early on I explained to you what the challenge we are dealing with. We need to limit the carrier frequency for efficient power, but then the data will be hurting. This is why we separated out those two, and therefore these traditional modulation techniques that you have probably heard of in your communication class are not really very applicable. I mean, they are applicable, they are still being used and papers being published, but the problem is that really they are not as efficient as they can be. So what before I get there, I also want to point out the fact that as we bring these coils very close to one another, we want to minimize the interference between the carrier that does the power transfer. It's a huge carrier, it is 100 volts, and it's 2 orders of magnitude larger than the other 2 carriers which are responsible for data. So one trick that we have used is this one. We use basically spiral planar coils that are facing one another for power transfer, because then we get a very good coupling between this implanted coil and this external coil, and then use vertical coils for data transfer. By doing that, even though the coupling between these 2 vertical data coils is not nearly as good as the power coil, but as I said, the receiver could be sensitive enough to detect that power. What is important is that two vertical coils that are completely symmetrical can ideally be designed to have zero interference, even though that's impossible in reality. But this nice technique can minimize your power carrier interference onto the data carrier, and therefore you can manage to deliver the data. Another very interesting trick is the figure 8 coil. The figure 8 coil is designed such that it has two windings that are opposite direction. So when you have a huge electromagnetic field induced by the power transmitter coil, the current that is induced on one half of this coil opposes the current induced in the other half, and they roughly cancel out each other. But when there are two figure 8 coils inducing or interacting with one another, then they see each other fairly well. So this is another technique that we have used and explained in the paper. But the question is that how can we excuse me, how can we push the power consumption even lower? And we came up with this idea of why not getting rid of the data carrier altogether, okay? And we are not the first to come up with this idea of getting rid of the carrier in order to transfer power. All of you have, or most of you might have heard about ultra-wideband, and there is a certain type of ultra-wideband called impulse radio ultra-wideband. In impulse radio ultra-wideband that has been basically invented and developed during late 90s at the University of Southern California, you use pulses, very short and narrow pulses to deliver data. If you have a pulse detected on the receiver, you have a 1. If you don't have a pulse, you have a 0. Or you can basically use combination of these pulses to deliver your data. Very smart technique. People had not used this technique because this is used in far field communication. People had not used this method in near field communication across inductive links. That's what we did. And basically the concept was really simple, that if you basically generate a pulse across the transmitter coil, it's like clunking a guitar string. On the receiver side, because these two tank circuits are resonating, on the receiver side, the result is this, okay? Now, the problem is that now I have a problem, well, and that gets rid of the carrier altogether, so I save power by getting rid of the carrier. The problem is that if I increase the quality factor of my receiver by reducing that resistance for good reasons, because if you reduce the quality, well, let me tell you first what the problem is. The problem is this tail. This tail is killing me. Because if I send a pulse, I have to wait for 1 millisecond for the tail of the pulse. If the quality factor of the receiver is high, I have to wait for this tail to die before I can send my next pulse. That limits my data rate to 1 kilobit per second. That's very low. That's not enough. If I lower the quality factor, then the pulse rapidly dies. The problem with lowering the quality factor is that I'm sure you have heard about seen the quality factor in your Circuit 101. If you have high quality factor, you have a narrow and short and a narrow band filter. If you lower the quality factor, you have a wide band filter. The problem with having a wide band filter on the data receiver side is that I have a huge power carrier that is interfering with my data. So if I do not use a narrow band filter, all of that power carrier interference will totally saturate my receiver. So the question is, how would you limit the bandwidth and use a high Q receiver without really basically and at the same time kill the tail? That was the problem that we were dealing with. And the answer is very simple. You use a second pulse to kill the tail of the first pulse. And this is what we call pulse harmonic modulation. Basically, we play with the harmonic frequencies of the initial pulse and use a second pulse that is applied at the right delay and the right amplitude to create an oscillation that is 180 degrees out of phase with the tail of the first oscillation. And when you use superposition, you get very nice oscillation on the receiver that is killed at the right time for the next pulse to occur. And again, I don't go through the detail, but you can see that the blue pulse is creating this oscillation, the red pulse is creating the red oscillation, the sum of these two is this one, and about 200 nanoseconds after the first pulse, I can transmit the next bit. Then we developed a transceiver based on pulse harmonic modulation technique. We implemented it in a very old 0.5 micrometer process because this was just a prototype, and this is the test setup. This is basically a gigabit that can send a random serial data bit stream that was going across these figure 8 coils. As I said, figure 8 coils are the ones that are resistant to power carrier interference. And then this one will receive the data and analyze it, and then these two are the data are compared to see how much bit error rate we get. And here is a nice comparison between when you do not use pulse harmonic modulation, when you send only one pulse per bit, and when you use pulse harmonic modulation. Basically, you use those two pulses per bit, and this is the received signal. You can see that basically the data is totally lost because of the interference between two adjacent pulses. Here, the data is very nicely maintained and it can be recovered. And here is the proof. Next, we built a more advanced version of that, and we have basically achieved 20 megabit per second with a bit error rate of 10 to the power minus 7, which is the highest rate ever reported today across an inductive link. This is a comparison with other similar work. We did our first version, achieved 10.2 megabit per second. The most recent one is a 20 megabit per second link with really dismal power consumption, because generating that short pulse or two pulses is much less power consuming than generating a carrier signal and basically going head to head with the power carrier, which is huge. And the transmission of data and power together is also very important. To the interest of time, I don't go through this. This is a whole another mechanism which we call power delay modulation. In this technique, we use, because see, your power carrier is always on top of the data carrier. On the receiver side, you get a huge interference from the power carrier. The trick here is that in order to deliver data and power at the same time, we thought, okay, why don't we use the interference from power carrier, which happens to be at 13.56 megahertz, for delivering data. How do we do this? Is presented here, that the interference from the data from the power carrier is a nasty sinusoid that is at 13.56 megahertz, and that is undesired. You don't want to really get that sinusoid across your receiver, but it comes in because your coils are coupled into one another. So we thought, how can we use that interference, which is inevitable, for data transfer? And the answer which my student came up with was that if we hit that interference with a sharp pulse, so similar to pulse harmonic modulation, this is a carrierless data transfer. What we do is that we hit right on the, not on the head, but the power carrier interference at the zero crossing. That is when basically the power carrier is crossing a zero, therefore it's as if it doesn't exist. That is when the power carrier interference is the weakest. So we hit the power carrier right there when it's the weakest, and that pulse, after interfering with the power carrier, can slightly shift the zero crossing. That's enough for us to detect whether a 1 is coming or a 0 is coming. So this is why we call this method pulse delay modulation. When the zero crossing is right where it has to occur, and it's very easy for us to detect that because I can get the power carrier and the timing of the power carrier from the receiver code, from the power receiver code. I have the exact timing of the receive power carrier. Now, if I also look at the interference from the data carrier and compare the interference at the data carrier with the power carrier, then I can see whether the zero crossing is where it was supposed to be or it has shifted a little bit. And it only shifts when I transmit those data pulses right on time for them to then shift the power carrier interference. This is the mechanism, the mindset behind power transfer pulse delay modulation. And I skipped the equations. These are some of the details that you can see in the paper. Again, we built a transceiver based on that and presented it in a journal paper that is under review. So there is not much time left for me to, basically this was then a real tutorial because I just covered the data and power transfer. Hopefully now you are basically learned a lot about how to deal with some of the challenges in delivering data and power to an implantable device, but wireless neural recording system to deliver the information from inside the body outside, or wireless data transmission in order to stimulate, basically deliver information and power, for example, for deep brain stimulation, or some of the applications of what I talked about here. And probably it's time to stop and see if there are any quick questions. Thank you very much. Any questions before we go to lunch?
So how do you shield the implantable device from the other neural activities going on in the brain? And I guess some of the electromagnetic properties of cells.
Oh, those are extremely weak. Actually, the amplitude of your neural activity, of course, it's also different whether you are measuring it between inside the cell and outside the cell, or whether you are just outside the cell. The type of recording we do is called extracellular recording, meaning that we put the electrodes outside the cell, and the amplitude of the neural activity outside the cell is in the order of 1 millivolt. It's basically very, very weak. So there is a technique that not in my lab, but others are working on to basically use very, very sensitive receivers that are actually like hydrogen cooled. That's a technique called squid, to record non-invasively those very, very small and weak current pulses between neurons. But as far as interfering with, for example, what I explained, is really not a problem. You might ask if the magnetic field from outside generating current on the inside, and that is actually a method that is called transcranial magnetic stimulation. That requires a totally different type of code. They use actually that figure 8 code technique with the amplitude of power and the code dimensions that we are talking about here. That's not an issue. But very good question. In fact, transcranial magnetic stimulation is being used for therapeutic reasons, and are being used. There is an approved device for depression, so it is being used. Any other question? Yeah.
Were you using the 3-coil power transfer or the 2-coil?
Oh, we use all three of them. The thing is that based on that figure of merit, that tells you, so you calculate the figure of merit for your best 2-coil design. You do the same for your best 3-coil design and the best figure of merit you can get for your 4-coil design, because the peak saturates somewhere. It doesn't go anywhere above that. And then you compare these three figures of merit. The best one is your choice based on the amount of power you want to deliver, the size of the load that you have, the size of the source that you have. So as I said, what you design for delivering 1 kilowatt to charge an electric vehicle is a totally different design than the cochlear implant. So the answer is it totally depends on your application. Like the answer that John gave me about energy scaling.
Then with a Q of 150 on the internal coil, is that going to be sensitive to the magnetics from the external core for get it to be tuned that high? Or, how that high to be?
Very good question. Actually, yes. See, my answer is generally yes. Basically, when you have a high Q coil, you just pass by it and you change the quality factor of that coil. You bring, if I bring my head close to this, metallic shield, that quality factor changes. But first of all, the change is not huge. And secondly, what takes care of those modifications is our closed loop system. So what I did not explain here is that there is a closed loop system that basically adjusts the receiver circuit and the transmitter circuit for the best, to create the best situation around your inductive range. That's the topic of the whole other presentation. Yes, we move the frequency, we move the switching period of our data converter on the receiver, and even further, if you look at some of our papers, we even change that capacitor, the resonance capacitor, because we can tune that capacitor for the resonance to actually follow the carrier frequency or the changes in the environment. All of those are basically fair game for your smart circuit to change those for the best result at all times.
What are the considerations that you have to go for when you pick the technology now?
Very good question. At the moment, in my group, it's cost. We just go for the cheapest available technology that we can manage to build our device or our the circuit that we want in that technology. And the good thing is that for medical devices, really the speed is not a big issue. So there is not that much of interest, especially if you are cost conscious like me because of the budget situation. It's not a big interest to push towards deep submicron processes. There is an interest to go to deep submicron process not because of the speed but because of the voltage. What is exciting about 90 nanometer is that you can easily design circuits below 1 volt supply voltage. Actually, right now at ISSCC, for example, where the latest circuits are being presented, you can get basically now the competition is half a volt supply voltage. So the nano power, in fact, there is an ECG recording system being presented from the University of Michigan because I'm on the committee so look for biomedical, very exciting medical device integrated circuits coming up in February, ISSC 2014. There is a tens of nanowatts power consuming ECG recording system from University of Michigan. So that's a very interesting one. IMEC will have a paper. So to reach to those, so for example, in a 0.35 micrometer, the lowest I really push hard, and maybe I can operate my circuit at 1.8 volts supply voltage. With if I implement this at 90 nanometer, I can push it to half a volt. So that is the incentive the disadvantage is cost. Because this, for your information, a 5 by 5 millimeter through MOSIS, and this is actually quite expensive. It will cost about $8,000. If I want to do this at, because I recently got a quote, if I want to do the same thing in 90 nanometer, it's going to be $80,000. So one order of magnitude more expensive. Between 90 nanometer and 0.35, we are more than happy with this at the moment.
Yeah, I think you just mentioned it. I was going to ask the commercial potential of that, integrating nanotechnology here, but I think the cost is
yeah, so if by nanotechnology you mean the feature side of the transistors, yes, 90 nanometer is obviously nanotechnology. But if you are referring to, for example, growing those nanowires on a circuit like this, you can very well do that. All you need is a space and good processing skills to grow your nanowires on a 0.35. You know, I'm not a nanotechnology expert. I leave that to Vina to respond. I'm a circuit guy. So in my mind, the answer is yes. If you can design a very good biosensor that is implantable, for me to collaborate with Vina to develop the sensor for me, or the energy scavenging system of John, then we can just start the company. Any last question? Can I answer one more?
Yes.
Please.
The calculation was actually a second part to achieve the gain of the vibration.
Are you talking about the mechanical vibration? Yes, the pulse harmonic modulation. So there is a second part very similar to the first part. So every pulse you transmit creates an oscillation on the receiver side. Okay, so I send the first pulse to create an oscillation. It's like clunking a guitar string, and then I can leave it to die on its own. But what we do is that we send the first pulse to create that oscillation, and then when I no longer need it anymore because I want to send the next pulse, I send another pulse that creates an oscillation that is 180 degrees out of phase. So when this pulse adds, the tail of this pulse adds to the oscillation resulted by the second pulse, I totally kill the tail of that oscillation, and therefore my receiver will be ready to receive the next beat. That's how it is. The oscillation. That's right. But then because the you know at gigahertz it's probably not feasible, because the timing has to be extremely precise if my carrier is at gigahertz. But my resonance frequency of that receiver is about 50 megahertz. So at 50 megahertz, with today's very fast circuits, it's totally feasible. I mean, we have demonstrated 20 megabits per second using that technique. It's totally feasible to get the timing right, such that you send the second pulse to hit the tail of the first pulse exactly, so in a way that your oscillation doesn't go all the way to zero, but it's small enough for the next bit to be easily detected with low bit error rate. We have already demonstrated. Yes, yes, and you can actually adjust the as I said, the capacitor can be adjusted to tune this dynamically based on the environmental situation. Thank you very much.
Okay, that's time to say